200 anomaly flags, all of them legitimate, all of them real. The AI had flagged every deviation from baseline across the entire network segment. It had done exactly what it was designed to do. Kara looked at them for 3 hours. Then she looked at one specific alert, one of the lowest confidence flags in the entire set, and called an emergency maintenance window. That alert, the one with the lowest confidence score in the entire set, was the precursor to a cascading failure that would have taken the primary data center offline for 9 hours. The AI flagged 200 anomalies correctly. Only one of them was about to bring everything down. And the reason Kara knew which one was, before anything crashed, required a skill the AI does not have, and most organizations are not building. AI abnormality detection systems are built around a specific deliberate engineering choice: maximum recall. Recall means catching every real abnormality. It is the primary metric because a missed abnormality, a real problem that the AI did not flag, is operationally catastrophic. An extra flag, a real abnormality that turns out to be routine, is merely expensive in human attention. That trade-off made sense when human teams were the monitoring layer. An alert that requires 30 seconds of human review is cheap. A missed cascading failure is not. A 2025 Splunk report found enterprise networks averaged 4,000 AI anomalies flags per day, of which operations teams estimated fewer than 5% required immediate action. The 95% that did not were still real anomalies, just not significant ones. The problem is not that the AI is wrong. The problem is that recall optimized detection produces a volume that makes human triage structurally impossible without a second layer of intelligence, one that the AI was never trained to provide. That second layer is significance weighting, knowing not just that an abnormality is real, but whether it matters enough to act on immediately. That is the gap Kira was filling in her head with 40 years of experience, while 199 other alerts competed for her attention. AI abnormality detection models do not judge significance, they judge deviation. When a data point falls outside the model's definition of normal, it gets flagged. A 31% confidence flag means the model is 21% certain the deviation is real. It says nothing about whether the deviation matters. That distinction between a deviation being real and a deviation being significant is the gap that creates Kira's problem, and it is a gap that is structural, not accidental. Kira had been working that specific network topology for 4 years. She had internalized its blast radius architecture, which segment had automatic failover, which ones didn't, and which single interconnect, if it failed, would cascade to the primary data center. When she saw a 31% confidence flag at that interconnect, she did not see a low priority alert. She saw the highest significance alert on the dashboard because she knew what that location meant for everything downstream. The hybrid model is not fewer alerts. It is the same alert, weighted differently. AI handles recall, catching every abnormality with speed and coverage no human team can match. Humans supply significance, knowing which of those abnormalities is worth acting on immediately based on where it sits in the topology. Without the human layer, 200 correct alerts is not comprehensive coverage. It is a noise problem that makes the signal invisible. Kira moved through the alert list in 40 minutes. She was not reading the alert descriptions, she was reading locations, cross-referencing each flag against the topology map she had memorized across 4 years of operating the same infrastructure. 187 alerts, redundant segments, automatic failover, self-resolving. 11. Limited redundancy, words monitoring. 2. In zones where failure propagates upstream. One of those 2 was the 31% confidence flag at the primary interconnect. The 31% confidence score was technically correct. Individual microbursts on this interconnect were routine. What the confidence score did not capture was the acceleration, 6 hours of frequency doubling every 90 minutes. The AI had flagged the anomaly correctly. He had not flagged the trend correctly, because trained analysis across the full 6-hour window was not in its detection model. At the current rate, the interconnect buffer would overflow in 4 hours. The BGP cascade would follow. The data center would go offline. Kira escalated at hour 3. The maintenance window was approved at hour 3:30. The interconnect was stabilized in 23 minutes. 9 hours of potential outage, 23 minutes of planned maintenance, 627 minutes of difference, because one engineer looked at the right alerts. If this is the kind of thing your team needs to think about, subscribe now. Next week goes deeper. What Kira was doing has a name in network reliability engineering: Topology-Aware Alert Triage. It is the practice of weighting alerts not by their AI confidence score, which measures how certain the model is that a deviation is real, but by their topological significance, which determines how dangerous the deviation location makes it. Confidence and significance are different things. The AI produces the first, the engineer must supply the second. The framework Kira was applying can be taught and documented. It requires 3 questions, a sequence. First, where is this abnormality in the topology? Not what is deviating. Where is the deviation occurring relative to the network redundancy architecture and upstream dependencies? Second, what is the blast radius if this abnormality progresses? If this specific location fails, what fails downstream? An anomaly whose blast radius includes a primary data center is categorically different from one whose blast radius is a single non-critical workload. Third, what is the acceleration trend? Is the anomaly stable, platooning, or worsening at an increasing rate? A low confidence alert that is accelerating is more operationally dangerous than the high confidence alert that has been stable for 12 hours. The engineers who will matter most are not the ones who configure abnormality thresholds. AI configures thresholds. They are the ones who can answer those 3 questions instantly for any alert, because they know the topology well enough that the blast radius map is internalized, not consulted. Kira's knowledge took 4 years to build. It does not need to take 4 years to transfer. The organizations building better are documenting their blast radius architecture now, before Kira leaves and takes that map with her. The AI Anomaly Detection System of 2028 will not just flag deviations, they will weight them. The integration of topological significance into AI abnormality scoring is already underway. Cisco's most recent AI Ops update includes an experimental blast radius correlation feature, mapping each anomaly to the network topology and scoring it against known redundancy boundaries. Juniper's Mist AI roadmap includes Topology-Aware confidence weighting in its 2026 release schedule. This is how the gap closes. An engineer identifies what the AI cannot do. She develops a methodology. The methodology gets formalized. It gets integrated into the model. Then new gaps open because the network changes and the model's topology map becomes stale, and someone needs to maintain the significance architecture that the AI is now depending on. The roles being built right now are not the ones that watch AI alerts. They are the roles that teach AI what significance means. Alert significance architect, who formalizes the blast radius topology into machine-readable frameworks. Topology intelligence analyst, who maintain and update that framework as the network changes. Anomaly triage specialist, who bridge the AI's output and the operations team's capacity, translating 200 alerts into the 5 that need immediate action. Kira did all 3 informally in her head for 4 years. The organizations building better know those 3 things needs to be 3 roles, and that Kira's mental model needs to be in a system before it lives with her. Kira filed the incident report on a Friday afternoon. In the note field, she added something that had never appeared in an incident report at that organization before: a 3-paragraph description of the triage methodology she had used. Not the technical details of the anomaly, the method for finding it. She had been applying that method for 4 years. She had never written it down before. Nobody had asked her to. After this incident, someone did. The AI flagged 200 anomalies. She found the one that mattered. Not because she looked at the loudest alert, because she knew the map. Drop a comment in your environment right now. If the AI flagged 200 alerts, how would you find the one that mattered? What is your triage method? Because if this answer is solved by confidence score and starts at the top, this video is for you. And if you already have a better method, I want to know what it is, because that method belongs in the comments, not just in your head. Next week, an AI monitoring system that had built a precise baseline of normal network behavior, and then the network changed. New application, new traffic pattern, new load distribution. The AI kept comparing everything against how the network used to behave. It kept flagging the new normal, anomalous, and it missed the actual failure developing against the new baseline. The engineer who figured out what had happened and what that means for every organization running AI monitoring in a network that changes. Share this with the engineer on your team who is triaging your AI alert right now. How they are doing it matters more than any threshold in that model.